ME 347, Example 9. A Boeing 727-200 jet transport with a gross weight of 150,000 pounds force, wing planform area of 1,600 square feet, wing aspect ratio, which is the ratio of wingspan squared to planform area, of 6.5, and at an angle of attack of 0 degrees, is cruising at a velocity of 200 miles per hour at sea level. Below a Mach number of 0.6, the drag coefficient at zero lift has been determined to be approximately 0.0182. For part A, calculate the lift coefficient. For part B, calculate the velocity at an altitude of 30,000 feet. For part C, estimate the drag coefficient using an induced drag correlation. Finally, for part D, calculate the thrust and power required to overcome drag. For this problem, we will assume steady flight through quiescent air with negligible buoyancy forces. Also, we assume a Newtonian fluid with constant air properties at each altitude, based on the U.S. standard atmosphere. Finally, we assume that the lift coefficient is constant at both altitudes, and that there are negligible compressible effects for both coefficients. For part A, begin by drawing a free body diagram for the plane in steady flight. Thus, the velocity and altitude are constant. Then, applying our force balance in the z direction, where the sum of the forces are 0, we get that the lift and buoyancy force are equal to the weight of the plane. For these conditions, where the average density of the plane is 3 orders of magnitude greater than the density of the surrounding air, it is reasonable to neglect the buoyancy force. Substituting in our definition for lift in terms of the lift coefficient based on the planform area, defined as the maximum projected area of the wings, we solve for a lift coefficient of 0.917. This is a typical value for modern aircraft. For part B, we want to solve for the velocity at a cruising altitude of 30,000 feet. As a first approximation, we will assume that the wing flaps are in the same position and the lift coefficient is constant with Reynolds number. Based on this, the velocity will scale as the square of the ratio of the density at each elevation. Since the density decreases as we go upwards through the atmosphere, which can be thought of as a sea of air, the cruising velocity increases significantly to 327 miles per hour. Note that the properties for the U.S. standard atmosphere can be obtained from Table 8.3 in your textbook. For part C, we estimate the drag coefficient by using a correlation to include the induced drag due to trailing vortices generated at the wingtips. Note that the induced drag increases as the lift increases because there is a greater pressure differential generating the vortices. Also, the induced drag decreases with aspect ratio because for longer wings, there is more span to generate lift compared to the trailing vortices. Adding the induced drag to the drag at zero lift given in the problem statement, we get a total drag of 0.0594. Note that this drag is the same for both elevations because we are assuming a constant lift coefficient. Finally, for part D, we calculate the thrust and power for both elevations. We begin by referring back to our free body diagram from part A and apply a force balance in the x direction. Once again, for steady flight, the sum of the forces are 0, so we get that the thrust is equal to the drag. Substituting in our definition of drag based on the drag coefficient, we have an equation to solve for thrust. To simplify our calculations, we then divide by the weight in terms of the lift coefficient from part A to get that the ratio of thrust to weight is equal to the ratio of drag and lift coefficients, which is 0.065 for our case. Substituting in, we get that the thrust is 9,700 pounds force for both altitudes. Note that jet engines burn fuel at a rate proportional to the thrust delivered. Thus, for constant lift and drag coefficients, the total energy required for any given flight is the same. Finally, to calculate the power, we multiply the thrust by the velocity. Since the cruising speed increases, the power increases from 5,170 horsepower at sea level to 8,460 horsepower at 30,000 feet. Thus, the engines will need to produce more power while cruising at high altitude to complete the flight in a shorter amount of time.